So, we have started, we have ended the last class with actually Poisson distributed graphs, if you remember. Okay. And what was the interesting features we have shown in Poisson distributed graph is that Z 0 x is equal to G 1 x. Okay. So, G 0 is showing the degree distribution if you come pick up a random node, and G 1 is showing the degree distribution if you pick up a random edge and go to a random node and go to the node following that random edge. Okay. So, what will be Z 2 then? Can we calculate Z 2? So, Z 1 is any other physical significance? No, we have many physical significance. We will come to it, that what these generating functions can obtain. Like I will tell you something very non-intuitive, that from these generating functions perhaps you can calculate. So, if you have a flooding in the networks, from these generating functions you can estimate the amount of nodes covered through flooding. Okay. Given an arbitrary topology and I am executing flooding in the network, what is the amount of nodes covered by the network. So, you can have a lot of implications of this generating function. I will just tell you a sum, of which giant component is 1. Okay. You can perhaps you can, we will see that we can calculate the diameter.
How do you relate this particular thing with like picking up a random node or random edge and going to another random node? How do you relate that with giant components?
We will come to it. Okay. Do not worry, we will come to it. Okay. So, Z 2 is Z 1 is Z, okay, and Z 2 will be. So, you can just see that how do you calculate Z 2? Z 0. So, what happens? Z 0 x basically gives you e to the power z into e to the power z x minus 1. So, this square at x is equal to 1 gives us z square. Okay. So, z 2 is z square. Okay. Okay. Take the next one, exponentially distributed graphs. Okay. So, here p k is equal to 1 minus e to the power a kappa, that is exponent kappa. Okay. So, this is how exponential distributed graphs, this is the function which you get. Okay. So, what will be G 0 x? One minus summation k is equal to 0 to infinity e to the power minus k kappa into x to the power k, because this part is independent of k. So, it comes out as common for all. So, I can write it . minus k by kappa x to the power k. Okay. So, this is the expanded form. I have just written that expanded form in a compressed version. Agreed? Any problem?
Which one is k and which one is x?
Yeah, these are kappa. Kappa, 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 kappa and kappa. Okay. So, this is kappa and this is kappa. Okay. Yeah, Karishma, what is the problem? Bolo. It's okay. So, fine. Any question? So, this line now come to this line. This line becomes 1 minus e to the power 1 by kappa summation k is equal to 0 to infinity e x e to the power 1 minus kappa x k. Okay. Okay, no problem. So, expand this term, this is 1 when k is equal to 0, 1 plus e to the power 1 minus kappa x plus e to the power 1 minus kappa x whole square okay. It goes on like that. I guess no problem. So, this part is what is this expansion of? Huh? So, this basically becomes 1 minus e to the power minus 1 by kappa into x. Okay. So, that is how you get G 0 x. So, I do not know how to, my handwriting is bad. So, this is kappa and this is x. So, do not mix both.
So, this expansion will be valid only if that function less than 4. What's actually x? The polynomial is dependent on.
So, yeah, I will go for G 0 1 perhaps. Okay. So, for all practical purpose when we expand we try to, when we make it constant we do z 0 1. So, it will depend upon there may be cases where you do z 0 2, then you have to see whether this holds or not. Okay. So, now can you calculate G 1 x? What is G 1 x? Tell me. 1 by z G 0 dash x, if you remember. Okay. G 1 x is 1 by z 0 G 1 dash x, G 0 dash x. Okay. Clear? So, that will be equal to, so this term becomes, the up top term is constant,
minus 1 by that.
what happens?
That will be minus 1 by 1 minus e to the power minus whole square.
So, it will be basically 1 minus kappa whole square. But there is a z out here. Okay. It will come, just you do not worry. If you take z, so this gives the numerator square. Now, you do the z 0 dash 1, then you will see it comes. Okay. Okay. So, given this, can you calculate z 2? Z 2 is again z 0. Okay. So, what is z 0 dash x? Let us write, because the top stays as it is, the bottom hmm, 1 minus e to the power whole square, and what comes here? It will become a plus, and plus what? Okay. So, I have basically to take y is equal to x e to the power minus 1 by kappa. Then you can do it 1 minus y gives us basically 1 minus 1 y gives a minus 1. So, accordingly you get it. I think this is fine. Okay. So, then what happens? You have to do one more. You have to do one more time difference. So, this again becomes 1 minus x e to the power 1 minus kappa cube, and here it what comes? Minus 2, no, plus 2. It becomes plus the same way, it becomes plus 2, then okay. So, at x is equal to 1. So, then it becomes, see 1 as soon as you make x is equal to 1, it goes 1 at least vanishes. So, it will be e to the power 1 minus kappa 2 1 minus e to the power 1 minus kappa whole square. Okay. So, from this, just for your sake, we can also try to write z 1. Z 1 from this you can directly get, which is e to the power 1 minus kappa 1 minus e to the power 1 minus kappa. Okay. Z 1 comes directly from the first differentiation. I have done this z 0 dash x, then from there I have done this z 0 double dash x, and this gives you z 2 and this gives you z 1. Okay. Clear? Now, you can yourself answer this question. It will just go. Okay. So, again you see that z 2 is a sum. So, in this exponential distribution also you see z 2 is some power of 2, means it is square, is going square. Okay. So, it has not, it does not, it has a higher scale than random graphs. In random graph it was just square, it is 2 into square. Okay. Order is same, but scale is little higher. So, this way you can go on finding, okay, and you will find for various graphs what are the scales. What is interesting, what we will show after sometimes, that if you know Z2 and Z1 of a graph, okay, you can almost predict everything. Okay. You can almost you can predict the diameter just by knowing Z2 and Z1, you can predict the diameter. Okay. We will come to that calculation later, but is this clear? Okay. So, now this formalization or formalism can be further, you can extend this to various other arbitrary degree distributions. Okay. So, let us say that you have a network or you have a community of 1000 persons. I am just giving you in words, community of 1000 persons. Okay. So, each person knows 1 to 5 people. Okay, or 0 to 5 people, and number of persons knows 0 to 5 people is 0 is 86, 150, 260, 363, 238, 109 and 54. Okay. These are just numbers. Okay. So, you can sum up and you see this will come up to 1000. Okay. So, now can you write G0x of this? Can you write G0x of this network, of the network which of the friendship or acquaintance network which will be formed? Can you write the degree distribution, or can you write the generating function characterizing it degree distribution? Can you write? So, it will be simple, see 86 plus 150 x plus 363 x square plus 238 x cube plus 109 x 4 plus 54 x 5, all divided by 1000. So, immediately given any arbitrary graph, you have the generating function formalism, and then you can do all sorts of things. You can tell about the first neighbor, about the second neighbor, okay, about the component size, when this network will form large components, everything you can say. Okay. So, that is the power of this generating functions, that just given some information, you can analytically build up a lot of information, means you can extract a lot of information from very simple data. Okay. Very good. So, now what you can do, we can think that given the generating functions, given say G1 and G0, how can we find component size? Given G1 and G0, how can we find component size? Okay. So, I want to find the component size. So, first question I ask, that I take a random edge and I go to one node, Okay. I go to one node and what will be the component size. I go to a sense and this will form a component, basically this node will form a component. So, what will be the component size? This is my question. So think, if I take a random edge, I can reach a single node and nothing after that, this can happen, okay. Or I can reach a node with one neighbor, okay. So, what will be the component size of this? The exact component size of this. So, this is a recursive relation, that the components once I go there, I do not know, it will follow the same distribution as this. The component size will follow the same distribution as this. Yeah, we talk about independent relations. Okay. Good question, that we are thinking in terms of independent relations. Okay. So, it can have 2, it can have 3. So, let us write this way. I write h 1 x is equal to, you can reach a node which has no out degree, 0 out degree, that is z q 0 I tell. You can reach a node which has 1 out degree, that is q 1, and then once you reach a 1 out degree, then it is again h 1 x, okay, because then it follows the same distribution. Because these two are recursive relations, okay. Or you can have x means one node, one edge, x into q 2 into h 1 x whole square, because 2, this way it will go on, x into h 1 x, it is h 1 x k, no problem. Okay, very good. Yeah, so what is this q? What is this q? Probability that the outgoing edge q k is that probability that the outgoing that the number of outgoing edges of a node reached by randomly picking a edge. No, h 1 gives a component size if you come from a random edge. Okay. If you come from a random. So, what is this basically? This is basically G 1 Q 0, the components of Q 0s, Q k's are basically the components coefficients of Q G 1. The coefficients of Q k's, what is Q k? Probability that number of outgoing edge of a node reached by a randomly picking edge reached by randomly picking an edge, that is exactly what is G 1. So, the coefficients are coefficients of G 1. Okay. So, then what can we write this as x into no G 1 no think x into G, very good. Who told it? Great. G 1 h 1 x, thank you Kota. Okay. Okay. So, you get a recursive relation definition of H1x. Okay. But actually what you want? Actually what you want? You want to pick up a random node and see its component size, not a random edge. You want to pick up a random node and see its component size. That is what you want. So, you pick up a random node and you traverse one edge and then you see everything. Okay. So, picking up a random edge is equivalent to picking up a random node, traversing an edge and reaching Z0. So, we have told that this is G0 and this is G1. So, then what will be H0x? X picking up a random edge into, you can pick up a random edge. See, you can pick up a random edge by what? Okay, this is little involved, so I will tell you. You pick up a random node, you go here, okay, and you get here. You can get here 2, and this sorry. See, you can go to a random edge. First, let me write it, then you will. So, what you try to do is that if I pick up a random node, what will be the probability that there will be just one out, the probability there will be 2 out, the probability there will be n out. Okay. So, what is happening? What is that you have probability of 1 out, probability of 2 out, probability of n out, and that comes from pk, okay, p0, p1, p2, pk. Okay. Once you have that, immediately when you consider the out, what does that out means? That you have come from a random edge, and that gives you H1x. Immediately that gives you H1x. So, you get this equation H1x. Okay. So, what is happening? So, let us expand it and write H0x is equal to x into P0 plus x into P1. Okay. X into P1 means you plus x into P1 means you have one edge, you are here, you have one edge, okay. You are here, you have one edge. So, x, okay. And what is the probability that you will have one edge is P0, P1, I am sorry, if a P1, and then what will be the degree distribution of this, and this is exactly how you have reached here. Okay. So, again I tell that you are here, okay, and you can have one edge, two edge or n edge. Let us think you have one edge. So, you have one edge, so you traverse that edge, okay, and the probability that you have one edge is P1. Okay. So, x into P1, then once you reach here, you as if have reached here. So, that is H1. Okay. So, that way you go on writing. So, then you get this H0. No, H1x is x into G1 into xh, and this is x into G0. Expansion here is P0, here is Q0. Okay. So, these two are different. Okay. So, given these two equations, actually you can find out the component size. But as you can see, this is our one equation is tied with the other, okay, and it is difficult to solve this equation. Okay. It is difficult to solve this equation, but you can get many things, like let us try to find the average component size. What will be the average component size? What will be the average component size? What is H1? Tell me, let us write in words. Distribution of size of components reached from an arbitrary edge, okay, and this is distribution same from an arbitrary node. Okay. So, what will be the average component size when I pick up a random node?
The expected value of x0x.
What is that?
Summation of x into
No, tell me, if I am given a generating function, how do I find the average?
differential at 1.
Yeah. So, H0x where x is equal to 1. Extremely simple. Okay. So, S is basically H0 dash 1. Okay. So, let us try to do this. So, what will this be? I can do integration by parts G0 H1 x with x, okay, plus x will stay Z0 dash H1 x and H1 dash x. Am I correct? I think I am correct, at x is equal to 1. Okay. So, this becomes G0 H1 1 plus G0 dash H1 1 into H1 dash 1. Okay. So, what is H1 1? What is H1 1? Any generating function, when we put 1, normally should be 1 if it is properly. So, Z0 1 plus Z0 dash 1 into H1 dash 1. Okay. What is Z0 1? 1, simple, it is 1, 1 plus G0 dash 1 into H1 dash 1. Okay. So, now we have to find H1. So, H1 x is equal to x into G1 H1 x. Okay. So, what will happen? H1 dash x is, again we will have G1 H1 x, we might plus x stays G1 dash H1 x and H1 dash x. Am I correct? Okay. Vikash, is okay? Okay, very good. So, then you have to take at x is equal to 1 and immediately what you see that this becomes 1, h 1 is 1 and g 1 is 1. Okay. This becomes 1 and this becomes g 1 dash 1 into h 1 dash 1. Okay. So, I write h 1 dash 1 becomes this. So, h 1 dash 1 is g 1 dash 1 oh sorry yeah 1 by 1 minus g 1 dash 1. So, 1 and 2. Okay. No problem. So, once you have this 1 and 2, S becomes 1 plus g 0 dash 1 by 1 minus g 1 dash 1. Okay. Okay. So, we know what is Z 2 is. Z 1 is G 1 0 dash 1. Okay. Z 2 is, tell me what is Z 2. Yeah, and one step before G 0 dash 1 into G 1 dash 1. Okay. Z 2 was that, and from there you got this. Okay. So, actually Z 2 is Z 0 dash 1 is Z 1 into G 1 dash 1. Okay. So, what you can write G 1 dash 1 is Z 2 by Z 1, and if you substitute here it will be 1 plus Z 1 and 1 minus Z 2 by Z 1. Or if you want it in a more better way, Z 1 square Z 1 minus Z 2. Okay. Agreed? Nakul? That is fine. Very good. So, once you get this, can you think there is one more very interesting observations which we can make here? Can you tell me from this equation there is a very interesting observation we can make? Anybody?
G1 dash 1 should be smaller than 1.
Very good. So, the question is that what will happen when G 1 dash 1 becomes equal to 0? What is happening? If this becomes 0, then what is happening? Tell me. Yeah, very good. So, then S will tend to infinity. Yeah. Yeah, today you are batting extremely well. Yeah, very good. So, what is happening is as soon as you make 1 dash 1 minus Z 1 dash equal to 0, then this becomes infinity. Okay. And how, when can it become infinite? When can the average component size become infinite? When there is an existence of an infinite component. That means, when there is an existence of a giant component. So, this condition gives us the exact condition or exact formula where giant component emerges. Okay. And now, let us try to do it. What is G 1 dash 1? I want to write it in terms of KPK. So, let us go back and try to write G 1 x in terms of KPK. Okay. So, what is G 1 x in terms of KPK? It is summation of KPK x to the power k x to the k minus 1 by summation of KPK. Am I correct? This was G 1 x. Okay. KK. Am I correct? Okay. So, you can see that this is G 1 x, because G 1 x was that you not only the degree of not only the probability of k, but what is the degree of k, because you are reaching from a random edge. So, it depends that how many entries this node has. So, that is why you had these two terms. Okay. So, now let us do G 1 x dash x. Okay. What will this give? K into k minus 1 p k into x k minus 2, and below k p k stays. Okay. Agreed? Very good. So, now what is then G 1 dash 1? Summation of k into k minus 1 into p k by summation of k p k. Rahul, it is okay? Okay, very good. And this should be equal to 1 according to this formula. Okay. So, what happens is summation of k minus 1 p k minus summation of k p k should be equal to 0, and this is summation of k minus 2 p k equals to 0. Okay. So, it is the old equation, old formula, say, which we first derived intuitively, we can now derive more rigorously. Okay. The formula which we derived, or we just showed that this can be idea, that exactly is coming out here. Yeah.
K is always positive.
K is the degree, so it cannot be negative.
Pk is also positive.
Yeah, but k, that means what you see, that if k is somewhere around 2, if k is more than 2 for all k's, then this will be greater than 0. Okay. So, normally what you can say, if it is greater than 2, there is a high chance of having a giant component.
Not
because some will exceed 0.
Yeah.
P factor can balance it in.
Yeah, some will exceed 0. So, then what is happening? That means what is happening is, if you see this equation, if in this equation g dash s becomes greater than 1, then this becomes negative. So, it does not hold. So, anything beyond 0 does not hold.
Can we say that average value is close to 2?
No, we cannot say that. Means what we can say from this equation is that if there is no 0° nodes, 0° nodes and 1° nodes, then there will be a giant component. This much we can say. Okay. So, I come back to this equation once more and just clear some of the things. So, what will happen if this becomes negative? No, if this becomes negative and the entire thing becomes negative, it has no meaning. Okay, if this becomes negative, then component size becomes less than 1, which is not possible. If this becomes negative, component size becomes less than 1, which is not possible. Okay. So, what is happening? What is our premise? What is our premise? See, when we have done this, what is our premise? When we have calculated H 0 and H 1 or everything, our premise is a giant component does not exist. So, entire calculation is done based upon giant component does not exist. Okay. And as soon as we reach this edge, beyond that this equation breaks down. So, it is like a Big Bang concept. Okay. Believe me, Big Bang is also based upon these concepts, that a equation goes for certain time and then it breaks down. So, beyond that this equation simply does not hold. Okay. So, the next question which I can ask is that given a giant component, what will be the size of the other components? Okay. So, given a giant component, what will be the size of the other components? Component, what will be the size of the other components? So, if a giant component is there whose size is a giant component whose size is S. Okay. You have a giant component whose size is S. So, what will be H 0 1 then? Huh? No, average giant component size is S. Then what will be H 0 1? H 0 1 can no longer be unity, because H 0 1 is seeing the components 1 size, 0, 2 size, 3 size, and I am excluding the giant component from that calculation. Okay. What I am trying to do? I am trying to find out the average component size excluding the giant component. Then H 0 1 will be 1 minus S. I have to suitably normalize H 0 1. So, 1 minus S. Okay. So, come back to these two equations again, two master equations. See these two equations. Okay, I think I will write it for you once more, that let this stay H 1 x is equal to x g 1 H 1 x and H 0 x is equal to x g 0 H 1 x. Yeah, S is a fraction of nodes. Okay, so whose size means fraction of nodes. Very good, thank you. X is fraction of nodes. Very good. So, H 0 x is equal to x, you have this. So, tell me what will be, I put it here. Okay. So, 1 minus s is equal to G 0 H 1 1. So, if H 1 1 is equal to u, then 1 minus s G 0 u, where u is equal to G 1 u. Okay. So, let us try to find this. What will be this, Nisha? S, average S now. Tell me what will be average S? Moinak, how do you find, how did you find averages last time? Of what? Not H 1, H 0 dash 1. Okay. What extra should come here now? We have to normalize it with H 0 1, because we know that H 0 1 is not 1. Okay. That is why we have to normalize it by 1. Okay. Clear? So, then what is H 0 dash 1? Again from this you know it will be G 0, I write it H 1 1 plus G 0 dash H 1 1 into G 1 H 1 1, means unlike previous case, here we cannot just put H 1 1 is equal to 1, okay, and 1 minus G 1 dash H 1 1. And so, let us believe me this, okay. You can see this calculation, and this will become 1 plus z u square 1 minus s 1 minus G 1 dash u. Okay. Agreed? Okay. So, now what we can do, again we can go, this is the general equation we get, again we can go back to specialized graphs, okay, like random network, and see how this equation behaves, okay, which we will do in the next class. Thank you.